Stephan Hoyer to our
Greg. Craig?
Sorry about that. That the recording screen came on and I accidentally pressed leave the meeting. Sorry. Yeah. Welcome, Stephan Hoyer. And I'd like to acknowledge, I think most of us are here in Australia and we are all on unceded lands of the original Aboriginal people. I'm on the lands of the Wurundjeri people here in Melbourne, and I wish to acknowledge them as traditional owners and would like to pay my respects to their elders, past and present, and Aboriginal elders of other communities who may be here today. Our speaker today is Stephan Hoyer. He's a staff software engineer at Google Research, where he leads a team building artificial intelligence-based weather and climate models. His research spans the intersection of physics, numerical computing, and machine learning. Stephan has also made significant contributions to open source libraries for scientific computing in Python, including Xarray, NumPy, and JAX. He holds a PhD in physics from the University of California, Berkeley. So thanks so much, Stephan. Take it away.
All right. Thanks, Craig, for the introduction. So I'm speaking to you all from, actually calling in from California today, near San Francisco. So it's not a, well, and I'd be, I can answer questions afterwards, but also I'm happy to keep this a little informal. So if you have something, pressing that something that comes to mind, feel free to sort of raise your hands in the Zoom, and I'm happy to sort of answer questions kind of as they arise as well. So today I'm going to tell you about the work that I've been doing over the past couple of years with a team, mostly at Google Research, on sort of building a new atmospheric model that combines aspects of sort of traditional numerical simulations and machine learning. So first, I'd like to sort of acknowledge the large team that worked on this project, including a bunch of my colleagues at Google Research and collaborators at ECWF, MIT, and Google DeepMind.
Okay. It's okay. I can do it.
I think someone's unmuted. I don't know if you had a question there. All right, let me continue. So today, all right. So today, again, going to talk a little bit about the context here, which is, I guess, looking at just the past few years, we've seen that with a real AI revolution, it's arrived for weather forecasting. But I'm going to talk about sort of hybrid machine learning and physics models, which neural GCM is an example of. And then we're going to get into some of the results. And so I'm going to talk about the results both for ensemble weather prediction and climate modeling, and then sort of close by talking about the bigger picture. So to begin, let's look at the AI revolution for weather forecasting. Okay, so as I'm sure all of you know, simulation is how traditional weather and climate models work. And this is a paradigm that's been at least conceived of, more than 100 years ago, and that has really sort of paid off over the past 40, 50 years, when we've seen numerical weather prediction systems based on solving the equations of motion of the atmosphere and then other parts of the Earth system that have sort of steadily improved in accuracy at a rate of about one forecast day per decade, that they're more accurate. So it's a 7-day accurate forecast today is about as accurate as a 3-day forecast was about 40 years ago. And this is pretty remarkable. It's arguably the trend here. These models are maybe starting to saturate a little bit in terms of the accuracy gains that we see, say, in the most recent decade. Especially if you look at this chart, going out for the sort of the next 10 years since this paper, but it's still been a really remarkable rate of progress we've seen with simulation. Well, even more remarkable, perhaps, is the rate of progress we've seen on sort of forecast accuracy for AI weather models. So this is a chart of these, or the accuracy of these models that are, so instead of solving the equations of motion, now they're building a big AI model, a deep learning model of some kind, typically. And the accuracy of these models, sort of relative to the ECNWF IFS model, which is considered the best model for medium range weather prediction. And you can see, so starting with some initial experiments back in 2018 or 2019, the models were much worse than the state of the art. And then it's really shifted, and sort of slowly been some improvements over the past few years, going out to around 2022, when we saw this paper from Ryan Kiesler. The models were getting pretty close, maybe up 75%. That was kind of interesting. And then suddenly, just in the past year or two, we've seen sort of real explosion of AI models that suddenly, in terms of their at least in terms of their overall accuracy, are sort of at or exceeding the state of these best numerical weather predictions from ECNWF. And this work, particularly Pangu and GraphCast from DeepMind, these were published in Nature and Science last year. And organizations like ECNWF and NOAA are mobilizing very quickly to start operationalizing these new AI models in their because it's the accuracy is really kind of astonishing. So this has happened really fast, but these models are fantastic, and they have really good metrics in terms of overall metrics, like a root mean squared error for a multi-day prediction. But they have some issues, and probably the most prominent issue is that they make blurry forecasts at longer lead times. So if this is an example, I mean, I'm plotting some forecasts here from the DeepMind GraphCast model. And if you look at a 6-hour forecast in the model, it has a lot of these pretty sharp features that you can see that come out, and these corresponding to storms in the tropics. But if you look at even, say, a 24-hour forecast, things are a little bit blurrier, and a 10-day forecast, things are a lot blurrier. And so what we see is that these, especially at these longer lead times, these models are making progressively blurrier and blurrier forecasts, which may actually it can be an accurate forecast in terms of the average forecast, but it's not necessarily a useful forecast, because it doesn't capture the range of weather variability. Sort of eventually you run these out even longer, these models sort of turn to like a total blur, or they actually reach certain numerical instabilities and they just blow up. And so neither outcome is actually very informative. Eventually, these models just predict something looking very close to maybe climatology in the best case. And this comes in part, we sort of know why this is, because these models, they're deterministic models. They're trained to minimize a squared error. And when you minimize a squared error, in the face of sort of an unsolvable task, like say weather prediction for 10 plus days, models will get a better score by hedging their forecasts and predicting something closer to the mean of the distribution. So that's what they do, but it still makes these models, it's still not very satisfying. And particularly if we're interested in use cases going beyond a couple of days in the future, if we're interested in climate simulation, if we're interested in understanding the range of extreme weather scenarios, we need physically consistent forecasts. We need forecasts that will sample from the range of sort of plausible weather scenarios. So that's kind of the context for where I think some of these existing models are falling short. Okay, so let's talk now about hybrid models. So as we're looking at these new models for these new weather weather models and other sort of models for sort of different physical systems, we have a choice. And these new the new models are we might call pure machine learning models. And so here these models are so examples like this, like GraphCast and the Pangu weather, that have really remarkable accuracy in the past year. These are typically based on deep neural networks. On the other hand, we have physics-based models which are solving equations of motion on a grid. And this is like where traditional numerical weather prediction and sort of climate models fall. And each of these approaches has different strengths. So the strength of the pure machine learning approach is that these models are based on training data alone. So you don't actually need to know the equations you're solving. And in fact, you don't even necessarily have to formulate the problem perfectly. As long as you kind of get the data in there, you ask the models to make predictions. They will be directly optimized to predict exactly what you care about. So you can set up the model to predict weather some number of days in advance, and as long as you have a sufficient training data set and a sufficiently sort of the right sort of machine learning architecture with a neural net that has the right sort of that is powerful enough, and you sort of throw these at a bunch of, I mean, there's definitely a lot of art in getting these to perform well, but if you have enough data, you throw enough compute at it, you can really optimize a very accurate forecast. And if that's your goal, then it may be hard to do better than that. On the other hand, the physics-based models have different strengths, and the physics-based models, instead of relying on data, they rely only on physical laws. Now, there still can be some parameters inside physical laws that are maybe that maybe we don't know from first principles, but generally speaking, with the physics-based approaches, we know the equations we're solving. We don't have to worry about if the laws of physics are going to change in the future. We kind of trust that they won't, and that means that the models that we built here, they generalize by construction. And that's useful when you think about you say you'd like to be able to predict what happens to the atmosphere, even in a future climate change scenario, in sort of an extreme weather scenario, sort of scenarios that never been seen before. Maybe you launch a new satellite, you'd like to be able to predict what the satellite's going to what sort of measurements that satellite's going to make before we start collecting data. So there's strengths on that side too. And so hybrid models, and so that's like models like neural GCM, I'm going to tell you about today, fall in between. And the idea, at least in theory, is that we can blend the strengths of both approaches. So we can take a physics-based simulation and take the parts of the physics-based simulation that we most that we trust, such as the large, and typically it's the large-scale fluid motions of the atmosphere. So and then there are parts of the equations that we trust less, and those, and in a weather climate model, those will be the sort of small sort of subgrid scale parameterizations. And there's some uncertainty. So we're going to take the parts that we don't trust, we're going to replace those by machine learning, maybe try to learn some more accurate approximation or make something that runs faster. And ideally, we still sort of preserve the large scale physics as part of that. So we have something that can sort of blend together the strengths of both sides. All right, well, hybrid models, not entirely a new idea. Definitely not a new idea. In fact, I think the first successful hybrid models, I think there's a whole line of research on these models going back to at least 2018, not earlier. And there have actually been some nice examples of this in a climate context, but they've seemed to be hard to get to work well. So when you take an existing climate model and now you try to plug in a neural network to represent some of the processes, it often doesn't perform as well as you would hope. And these models have, even when they're able to, when these models are trained, and they plug back in, so the performance can often be pretty bad. The simulation often sort of blows up entirely. A lot of these models that have worked well have been done in pretty idealized settings. And when they're done in sort of more realistic settings, like sort of real world topography and so forth, the gains have actually been pretty small, especially pretty small compared to what you might expect from the accuracy of the neural network when you trained it. So what's going wrong? Well, so one of the big things that we did in this work is we think we have part of an answer for this, and that is that these hybrid models are typically optimizing for the wrong metric. They're doing something called offline learning. So let me tell you what that is and how we fix that. So in a sort of conventional hybrid modeling approach, we have the sort of physics we know and understand. We'll say that's the dynamical core that we trust. And then there's some unresolved physics, like the sort of the subgrid scale physics. We're going to replace that with a neural network, and we're going to use that to correct the state that comes out of the dynamical core. And so the procedure roughly is collect a bunch of examples of sort of states of the world, feed them through the physics simulation, the dynamical core, now we have inputs and outputs to the neural network. The outputs we might get from another simulation or from, say, a reanalysis data set. Or some sort of direct observations. And now we're going to try to sort of match up, try to tune the neural network to take the right inputs, produce the right outputs. And so in principle, that seems like a pretty reasonable thing to do. The challenge is that in practice, this is we're only training, well, all we're able to do in the setup is train the neural network to predict, to sort of step forward a single time step of the model. So say step forward, I don't know, maybe 30 minutes or an hour forward in time. Unfortunately, when we actually use these models, they're used in a very different context. So in practice, we're training for one time step, but at inference, we're going to run many, many time steps, maybe tens or hundreds of thousands of time steps to run out a climate simulation. And when the inference setup is very different from the training setup in a machine learning model, that introduces what's in the machine learning literature, we would call it sort of a test train skew. And the performance of the models, I mean, maybe not surprisingly, can be much worse if you're using them for something that's very different from how they were trained. So they only ever saw kind of like perfect inputs, basically, and now they're running on their own outputs, and that difference is often problematic, and that's why the online performance actually, when we run them in inference time, is very different from the offline performance at training for the single step. So how do we fix this? Well, in Neural GCM, what we did is we kind of went back to the drawing board and said that we are going to consider rewriting the physics simulator in a way such that we can optimize through the entire joint system, so that we can do this online online optimization. So what we did is we took a dynamical core. And we took sort of a standard procedure for solving the primitive equations of the Earth's atmosphere, and we rewrote it in a deep learning framework. We used JAX, which is a framework that's used at Google for training almost all of our large-scale AI models like Gemini. But in principle, it's very similar to what happens in PyTorch or Julia. And that is, because we wrote it in JAX, that means sort of two things. One, we can run it on a GPU or a Google TPU. And two, we can optimize through the dynamical core, just like we optimize through the neural network, because the model supports automatic differentiation. So now that we have that, we can do training and inference both over many time steps. Now in practice, we still will train and do inference sometimes over different times. We might only do training over maybe a few hundred time steps. So say make a weather over the time it takes to make a weather forecast over a handful of days. There are other reasons why it's hard to train on, say, like a sort of much longer timescales, but the gap between training and inference is much smaller. And that means that because we're able to optimize the model to see its own outputs, it makes better predictions when we do that to make an actual forecast. So that's the setup. And now can I show you sort of an overall picture of how this model looks. So it's the first differentiable hybrid model for the Earth's atmosphere. And what that means is that we, again, combine this dynamical core, which we wrote in JAX, with a neural network only solving the so-called physics, the subgrid physics of the atmosphere. And that's processes like solar radiation, clouds, rain, and interactions with the land surface. And we're going to kind of basically add up contributions from the dynamical core and this sort of learned neural network, and plug those into an ODE solver in order to run our GCM. Now, this is very similar to the standard formulation for how general circulation models work. That's why we called it Neural GCM. Now, in order to train this thing, we're going to use kind of the standard procedure that's used now for these global AI weather models, and that is we're going to sort of sample short movies of sort of weather from ECWF's Era 5 reanalysis. And so these are the sort of the full 3D fields from Era 5, and these give us both sort of the inputs and the outputs of our model in terms of the prognostic variables of the atmosphere, like the wind speed, temperature, and the different moisture species. And then we also are going to feed in as additional inputs to our model. We feed in forcing conditions, which here is the current solar radiation and sea surface temperature. And we also feed in noise to our models as well. So our spatial temporally correlated noise, which our model can use to sample over, which our model can use to sort of in order to make sort of stochastic or ensemble predictions. In cases where we want to be sort of seeing uncertainty. Okay. So that's kind of the quick overview of kind of the motivation and kind of what neural GCM looks like. Let me talk about the results. So first, again, about ensemble weather prediction. So the first result, which we're very excited about, is that this is the first machine learning model that's been able to beat ECWF's ensemble weather prediction forecast on most metrics. And here, here, for example, we can look at the error on the 500 millibar height in terms of the root mean squared error and how that increases as a function of the lead time. And what you see is that these in gray and silver. In gray, you have the ECWF's model, which is considered the best in the world, and in blue, you have neural GCM, which is a little better than ECWF. Now, and then both these ensemble models are sort of much better than if you tried to just do a deterministic weather forecast, which is mostly what's been done in the past. So that's what models like the ECWF's high resolution simulation or GraphCast do. They just sample sort of one trajectory of weather, but actually making a probabilistic prediction, then averaging and then averaging afterwards is much better. We can also compare on sort of probabilistic metrics like this CRPS score, and again, we look a little favorable compared to ECWF. Now there's also kind of a whole range of different metrics you might look at, different levels and different variables. So we also sort of a kind of related project that I've worked on with some of my colleagues at Google is WeatherBench 2. And this is a project we have an interactive website that kind of goes through all these variables, and you can compare all these different new AI weather models and baselines and really see how they add up to each other. We're pleased that right now neural GCM models are kind of like the winners on this on these metrics, especially for the long term and sort of the ensemble weather prediction. It achieves the best scores. Okay. So that's what the scores, but how do these models look? Are they like realistic weather scenarios? So here I have kind of the audience challenge, and I think I'll be helped, I think, by the poor Zoom connection, which will make it harder for you to see the details in my little movies of the weather forecasts. So kind of to prove to you that these models are sort of reasonable. So I'm showing here 3 different simulations. 2 of these are ensemble weather forecasts from 15-day weather forecasts from neural GCM. One is ground truth here from ECWS, from the ERA 5 reanalysis. So you can take a look at these. I'm going to ask you in a minute to guess, or at least to think in your head which one is real and which one is fake. And 2 of them are fake, 1 of them is real. So which one is? So if we freeze this at +5 days, you see this. I picked this snapshot because each of them has a hurricane that's hitting the Gulf Coast of sort of the southern United States. If you look at +15 days, you see each of these scenarios has kind of spawn off into a different sample from the trajectory from the sort of the range of sort of plausible weather scenarios. Now they've all kind of diverged. Okay, so maybe think about these. Which one you think is real? I'll let you think that in your head. Is option A real, B real, or C real? Okay, big reveal. Option C was ERA 5. If you look closely, I think you can see it in the static images. There are a few high resolution features that we're not quite getting perfectly right. but we're pretty close. And part of that's just the limitations of our model. This is the kind of the native grid of our model and doesn't quite perfectly resolve all the finest resolution details. But it's getting pretty close. So I think generally we're doing a pretty good job of sampling from the realistic range of weather scenarios. And again, because we're pretty close, we can do things like simulate plausible looking tropical cyclones. So we can do this. So here's again the tropical cyclone hitting the southern coast of the United States. And if we sample, so ECWF was running a 50-member ensemble, and you can see what kind of where the trajectories we're in of all these sort of 50 different tropical cyclone tracks and sort of like where they end up. You compare this, and we can do the same scenario in Neural GCM, and we get a pretty similar looking range of different scenarios for where that tropical cyclone might go. And again, this is pretty remarkable because the new Neural GCM model it's an AI model, and it runs on a much coarser grid than ECWF. It runs on here about 140 kilometer resolution grid versus ECWF, which is about a 9 kilometer grid. And because of that, and because we're running on GPUs or TPUs, it's also much sort of dramatically cheaper, roughly in terms of compute. It's something like 16 cents versus $5,000 per forecast to sort of run the compute that's kind of shown in this image here. So it's a sort of really fast and accurate model that we can do. For example, if we wanted to make really large ensembles, that's actually very affordable to do now. Okay, so let me talk about. Let me sort of switch gears now and talk a little bit about what we've started to do with climate modeling. Okay, so because Neural GCM is an atmospheric model, so it's not a full climate model. But if we prescribe sea surface temperature, we sort of hold the boundaries constant with sort of observed observed weather from the past, we can run our atmosphere model out for longer periods of time. And so this looks similar to what's done in for atmosphere only climate models. We'll compare to a few of those in a minute, like an AMIP run. So again, by holding the sea surface temperature, we supply sort of historical sea ice concentration, sea surface temperature, and total incident solar radiation. Now we can run out these. We can sort of run the Neural GCM out for longer periods of time. If we do this, what you see is that Neural GCM sort of samples out. It's a little hard to see here, but in sort of light blue, I have these are different trajectories of weather, basically, over the course of a 1-year simulation. And you see they all get the seasonal cycle approximately correct for global mean temperature. And if you average them, the average is very close to is like a very smooth curve over the entire year. And it looks pretty similar to the ERA 5 in orange. They're the actual observations of global mean temperature over 2020. And we should perhaps expect this model to do well because again, it did see the real sea surface temperature observations, but the atmosphere did a pretty reasonable thing, which is actually pretty exciting. This is a first for AI climate models. In the past, have sort of really struggled to go past even a few months. We can compare again to like something like climatology, which of course like the average of the past 30 years. Again, because the oceans are warmer, we see that the model has learned to predict a warmer atmosphere as well. It's pretty close to observations. So let me show you a few more examples of this and what sort of what we've done with this. So we can compare to the bias for different weather variables to sort of state-of-the-art climate models and kind of next generation climate models like a global storm resolving model. So here I'm comparing Neural GCM to XShield. XShield is a model from the Geophysical Fluid Dynamics Lab at NOAA. That's kind of like the American weather model, except run at even higher resolution for climate configuration. And here we can look at bias in terms of the sort of total water in a vertically integrated water and at each location in the atmosphere, and just kind of average that over the course of a whole year, a year that was not in our training data set. And we see here that neural GCM is like lower bias by about it's about I think about 30-40% lower bias. And again, this is the models here, because we're running on such coarser grids. Neural GCM is much faster. It simulates about sort of 70,000 times faster than real time. Runs on a single Google TPU chip, which you can rent for about $1 an hour on the cloud, versus the GFDL model, which runs very slow on a sort of a gigantic number, kind of a whole slice of a supercomputer. And cost-wise, this one, the Google models are like 8 cents per simulated year, versus about 1,000,000 times more expensive, about roughly 80,000-ish for the simulated year with the XShield model. Of course, this model is actually, because it costs $80,000 to simulate 1 year, they actually only simulated 1 year because it's so expensive. But we can calculate a whole range of different scenarios with neural GCM. That's pretty affordable. And not only can we get these, bias for sort of average quantities like precipitable water, right? We can also sample out other types of weather phenomena like tropical cyclones. And so if we run the tropical cyclones for 2020, we see that neural GCM simulates a range of reasonable tropical cyclone scenarios that look like they're happening around the same place, and we get about as many as we actually observed in the real world. 83 versus 86. And we can also, of course, now we neural GCM is really cheap. We can do this a bunch of times. And we can compare to sort of historical patterns we see in tropical cyclones as well. So we can do this 34 times, corresponding to 34 years. And we see that it produces a map of sort of tropical cyclone count that actually looks quite similar to what was actually seen over the past 3 decades, with some a few small differences, but overall looks pretty close. At least I would have a hard time telling you sort of which one of these is sort of more reasonable as a set of predictions for what might happen for, say, 1 year in the future. All right, and so this is kind of near-term predictions of climate. We also have been looking at longer-term predictions, so going out to multi-decadal prediction, again with prescribed sea surface temperature. Now the challenge here is that our models are not perfect. And some of our models do diverge. So sometimes you run the model out for a couple of decades, and then suddenly the model sort of blows up. Or other times you see that you run the model out, and after a few years you notice that it's getting slightly warmer and warmer each year, and eventually it looks pretty bad. It's off by a few degrees. So we haven't kind of solved those issues completely, but we've got a model that works in many cases, and some versions of our models don't show these issues. Some, and that's often just like a different set of random parameters that we picked. We train a model multiple times. Sometimes we get lucky, or especially our models that are run on coarser grids tend to be more stable. That's probably because they take sort of fewer time steps to solve over the same period of time. So anyway, so the models that do work, we actually still can extract out sort of reasonable samples of future weather going out, again, projecting forward several decades. Now here we are kind of, we did train the neural GCM model on this data. We trained it on, again, this is 1980 through 2019, and this was in the training data set. But if you look at now at that said, if you look at the bias of neural GCM, in comparison to standard AMIT models, which these are CMIT models in an atmosphere only configuration, what you see is that neural GCM captures the same interannual variability in global mean temperature that you see sort of in the real world. That's the blue line here. And we can also sort of sample out a range of scenarios. From here, we do it with different initializing the model at different times. Similar to what we see in terms of the structure of the sort of the variations from year to year in an average of different AMIT runs. Now, this is actually, we average together the say about 20 different AMIT models because because climate models have pretty large biases. And so these models, the change, if you get a better answer if you average a bunch of them, or you look at the change between over the course of a few decades, and if you look at the absolute temperatures from these models, they're going to be off by a few degrees. And so if you compare the absolute temperatures, what you see, this is the average, say, for predictions of sort of weather near the surface at 850 millibars. Actually every sort of member of our neural GCM ensemble has a lower bias over this multi-decadal sort of AMIP run than all these AMIP ensemble members. And some of these different AMIP models have pretty large biases, either in either they're cold or they're warm. But even if you subtract away the global bias for each of these models, the error is still much larger than what we see for a neural GCM by a factor of about 3. Now, again, these models are also, of course, these AMIT models are closer to operational climate models. They're much cheaper. They still cost about $25-ish in compute to simulate 1 year. Whereas this neural GCM model, this is one of our models on an even coarser grid, about a 3-degree grid, because the models on the 140 kilometer model I was showing you earlier is not stable for this long, but it's sort of very, very, very cheap by comparison. Okay, so that's kind of that's most of it. So let's maybe take a step back and talk about maybe the bigger picture, and particularly for kind of where kind of see this field going. We've been talking about hybrid models, and I think the reason why I'm excited about hybrid models is part of this sort of bigger theme of research that we've been exploring here at Google on my team over the past few years. And this is looking at models that sort of blend together the strengths of machine learning and traditional computational algorithms. So I think what's exciting to see here with models like neural GCM is that we don't have to choose. We don't have to make a firm choice to say, like, I'm in the AI camp or I'm in the physics camp. We have this possibility to explore this sort of spectrum of possible model choices depending upon constraints like how much training data we have, how much we care about generalization versus just accuracy. And so I think I'm pretty excited about this. I think these are a really powerful tool when we want to sort of to optimize models more directly based on data. And I think that's really clear in the accuracy of short-term weather forecasts. But as we've seen with models like neural GCM, potentially also these sorts of ideas, at least some degree of AI, can also be helpful for going out to longer timescales like climate. I'll say that even within the range of, say, machine learning models or sort of pure physics models, not every model is like the same place in terms of how much AI versus physics. So if you look at a model like Pangu uses the transformers, that's pretty black box neural networks. If you, like, say, GraphCast, for example, makes predictions on a local graph, so it has this kind of built-in kind of notion of locality a little bit more. And it also makes autoregressive, sort of more forecasts that look a little closer to a physical simulation. And on the other hand, different types of physics models like numerical weather prediction model versus a climate model are building, and climate models have to simulate more different, simulate more physical processes because they need that fidelity on longer timescales. Whereas in a weather prediction model, you can get away with tuning things a little bit more. So it's a bit of a spectrum. I think it's really exciting to see that models like neural GCM sort of expand this kind of in between, sort of really spanning the full spectrum here. So let me give the summary, and then I'm happy to answer questions. So we've introduced this model, neural GCM. It's a hybrid physics and machine learning model of the Earth's atmosphere with state-of-the-art accuracy. We can look at 15-day weather forecasts that beat the European ensemble. And we have climate forecasts that on many variables are doing better than AMIP and global storm resolving models. It's a vastly faster and cheaper model. It's something like 1,000 to million-fold times sort of less expensive than sort of physics-based atmospheric models with comparable accuracy. And it's also much simpler. So it's still a big project to write neural GCM, but in terms of something like, say, lines of code, we've taken out the, if you compare neural GCM to the NOAA's FE3 model, which is used in XShield, it's something like 20 times fewer lines of code. So like 20,000 lines of code versus 40,000 lines of code. That's still a lot of code, but we've kind of moved a lot of the complexity into these sort of automatically learn parameters in the neural network. And that makes this, and that means we're able to build the state-of-the-art model in only, a small team of about 4 or 5 full-time sort of scientists over the course of like a year or two, which is a lot, which is relatively speaking pretty fast. So if you're interested in this, we have a preprint up on the archive that kind of goes into our results in much more detail, and we've also released open source code for this model as well, which you can find on GitHub. And with that, I guess I'll open it up to questions.
Thanks for that, Stephan. Kate, you've got your hand up. You've got a question? You want to jump in?
Hi. I don't know if you can see us, but thank you for the talk.
Yes.
Really interesting. I was just curious about how you're scoring these forecasts, because when you showed that 10-day image with the smoothing, surely your choice of scoring metric implies that you can end up with that score with that smoothing, where if you chose something that was more regionally specific, you might be able to force the model to create things that are more physical. I just wondered if you had a comment on that.
That's a great question. So, I mean, a lot of these scoring rules, we're doing things like kind of the standard, I guess, is things like a root mean squared error, or root mean squared error for like an ensemble mean is kind of, it's pretty interpretable, but it's not a great way to score forecasts. So we try to use things like these, like the CRPS score, which is for probabilistic forecasts, or other metrics, like we look at like the spectrum, things like that. The way that we actually sort of tuned our models to give reasonable predictions, basically, I mean, so we actually train we have some ways to sort of tune our loss functions to make good deterministic models, and other ways to make, but I think probably the future is trying to build stochastic models. So stochastic models, we are optimizing again to predict this probabilistic score, the CRPS, which rewards both predicting the average and the uncertainty in a probability distribution. So I think that's kind of the main, I don't know, like in terms of how we build these models, we try to optimize for things like that.
Yeah, maybe it would be interesting to see some like threshold weighted CRPSs for like extremes as well, I think, as a comment. Yeah, thank you.
Yeah, that would be, I think we should absolutely be doing that. We have not, there's a lot more evaluation to be done. I mean, I'll say that we have at least for evaluation, we have the archived ensemble forecast for 2020 that's saved in the cloud, if anyone wants to take a look at those.
Okay, thank you.
Jerry, I
All
think
right,
you
I
were
guess we
next up.
have somebody in building 125.
And
Okay, thank you. I was wondering if you could comment on what's the speed up between going from GPU to TPU.
Yep.
And the other thing I wanted to ask is, can you please explain the CRPS score?
Sure. So the GPU and TPU, honestly, pretty similar. We just have a lot of Google TPUs at Google. Those are sort of our own AI chips that we sort of fabricate ourselves. So we're not. But I mean, GPUs and TPUs, I think, pretty at a very high level. They both have a lot of matrix multiplication compute, which is great for neural networks. Actually, also great for implementing spectral dynamical cores. Also, that's part of why we use the spectral methods, because there's a lot of matrix multiplication in there. So pretty similar, but that and they're somewhat faster than CPUs. The main, I think the main, and that's, I don't know, maybe things like tenfold faster. The main reason why our models are faster is because we use such coarser grids. The CRPS score is a continuous ranked probability score. And this is kind of a standard method for evaluating weather forecasts. And it's also been used a bit recently for also in some cases for sort of optimizing machine learning weather forecasts, and it has a nice property, which is that it's a proper scoring rule, which means that it cannot be hedged. So you can't, if you really think that, if you have a belief about what the true distribution is of weather, of sort of your ensemble weather forecasts, you will get the best score if that true distribution is correct. You will get the best score by actually predicting that distribution. You will not get a better score by predicting something like a less extreme version of your forecast. So it's a good way to sort of tune these probabilistic forecasts. Okay.
Great.
I guess. Yeah.
Sorry, Stephen.
Jerry, do you want to go ahead?
Yeah. So you were saying that one of your breakthroughs is that you were able to get this to run past about 3 weeks, and I know a lot of these neural net climate models were blowing up, and anecdotally, some of the instability sometimes would come from the high latitudes, and I don't know if that was where you were seeing problems. I was curious, what did you do to get it to run out to multi-year timescales?
Good question. So in our case, most of our models, I don't know, they blow up in different places, but often it's like blowing up over mountains, and like very high, like over like the Andes or the Himalayas. I guess the main thing we did here, I mean, there are a few models recently. I will say that there is a model from Chris Brotherton's group at the Allen Institute called ACE that also has some really nice results recently in terms of sort of multi-year prediction with AI. They also have a preprint out on that over the past that came out, I think, in sort of late last year. I think the main thing is sort of how we train the model. So we didn't train it using this root mean squared error or the squared error. We have sort of our deterministic models. We do this. The main thing we do is we filter out the high spatial frequencies in computing the loss. And so what this means is filtering means that the model is not penalized for getting a fine detail wrong in say when it makes a prediction several days out, and that so the models can make much less blurry predictions. We also do these predictions again. We ask our model. We actually do ask it to make say up to a 3-day weather prediction or a 5-day weather prediction instead of only. In some cases, some other models say only a 6 or 12 hours sort of forward in the time. So asking the model to make longer predictions in the future also helps them sort of see their own inputs and be a bit more stable as well. So there's kind of a whole handful of tricks. I mean, I will say that it's a little hard to say for sure what all the key factors were.
Yeah, so it sounds like the filtering may have been a key there, though, right?
Yeah, the filtering for sure was quite important. I mean, I'll say that we don't actually use that trick in the stochastic models.
Right. Yeah. All right, thanks.
Great. Craig?
Hey, Stephen, thanks so much. Great talk. We're a climate center here. Could you talk a little bit about, I didn't hear much about how you're modeling the CO2. You know, if we're going to do climate change, you've basically got to have a model of all the major greenhouse gases. Looks like you've done a fantastic job with water vapor, which is part of it. But you also need some sort of model of how, you know, the radiative impact of these greenhouse gases. Do you have plans to put those in, or is it kind of in there and I didn't notice from the
That's a great question. We don't do carbon dioxide currently.
Right.
And we would like to. And that's certainly something we'll have to solve if we want to go in the direction of building a real climate model. And there's kind of a few different ways we could do that. Potentially, we could actually sort of write like something like a traditional radiative transfer code and kind of put it in there as sort of producing the sort of inputs. Maybe the neural network sees the outputs of the radiative transfer code instead of just seeing like incident solar radiation. We could also create training data sets that have like carbon dioxide in them. Then you have to also have some training data set of some kind for future carbon dioxide levels, because we don't have that in the ERA5. But I think that's pretty important. I mean, maybe that kind of gets to we were talking about this earlier, but in terms of like kind of what we're hoping to do next, I'll say that I think that moving in the direction of kind of building things that look more like climate models. But I think especially, and what I'm really excited about is being able to do things like rapidly sample sort of realistic scenarios of sort of even current climate risk, say over the next year or so. We don't need carbon dioxide for that, so it's a little bit easier. We will need like an ocean and a land model of some kind. But I think that could already be pretty useful if we can say estimate do a better job of estimating the risk of, you know, I don't say like tropical cyclones, for example.
Just a quick follow-up on the stability question. Could you, like in NWP, a key to that is the way you do the time stepping. Are you doing implicit or explicit? Could you
Yes.
talk a little bit about what sort of time stepping scheme you use?
Yeah, so for the dynamical core, we use a pretty standard sort of split implicit explicit time stepping scheme. For the physics, that's sort of a fully explicit. So this is kind of like within the realm of, we also use kind of a larger time step for the neural net physics. So this is kind of roughly the flavor of how a lot of GCMs are built.
So with the time stepping, as it's doing the time stepping, you don't let the solver know about sort of the tendency at the future time versus the tendency at the current time. It only knows about the tendency from the current time. Is that right?
It only sees the physics tendency only gets updated once, say, every 30 minutes. And our internal time step on dynamics is typically shorter than that.
Right. Okay.
I'm pretty sure we could do more stable things. If it's just, I mean, it's kind of a little hard to say where the source of instability is. I will say that we could, if it was really in the dynamics, we could be doing better by doing a semi-implicit time stepping. That would kind of eliminate the instability issues. I think it's also the part of like the kind of the intersection of the numerics and the machine learning has a tendency to occasionally things kind of drift out of distribution, and the neural nets give kind of like pretty garbage results. And so there's a lot of stuff. I think this is one of the biggest kind of unsolved problems for this field is to figure out how to sort of reliably train models that are stable.
I don't know if you can see it. There's a question from Savin Shan.
Oh, I see that. Yes, in the chat.
Yeah.
So regarding tropical cyclone forecasts, has there been any improvement in terms of tropical cyclone intensity forecasts compared with conventional numerical weather prediction? That's a great question. I don't really have an answer for you, unfortunately, because I don't think we didn't actually quantitate. Well, we haven't really done quantitative comparisons of our tropical cyclone forecasts. We only have that kind of that 1 year of data in 2020, and that seemed like not a lot of data for making quantitative comparisons. We did do some looking at intensity in terms of like wind speed, and some of like the sort of the climate, for some of the climate simulations, and there it's kind of roughly in sort of a similar ballpark to what you have in terms of era 5 if you coarsen everything to a very coarse grid. But like honestly, it's a little hard to say for sure what we're seeing at 140 kilometer resolution is not great for tropical cyclones. So even if we match era 5 there, it's not clear if that's like the right target. So I think that's definitely an area to continue work. Okay, I guess I don't know which order this came in.
Hamish was first.
Hamish, yes.
Cool, thanks. Yeah, I had a really specific question. You had a slide on the 850 millibar temperature time series over maybe 40 years or something like that. And it seemed that the neural GCM kind of converges towards the era 5 after about the late 90s. And there's a kind of a gap in around sort of the 80s and the 90s where it's not doing so well. I was just wondering if that's, you know, multi-decadal variability that's not being picked up, or what's the reason for that? Do you know?
That's a great question. I don't know. I mean, I will say that like it's again like the neural GCM did train on this data as well, so it's not exactly like it has kind of seen all these. I mean, it didn't see the exact. I mean, it's arriving with a different weather, you know, atmospheric state, but it did see the ocean temperatures before in the training data set.
Yeah.
I'm not. I mean, of course, the model, also the neural GCM model, the neural net only sees kind of one vertical column of the atmosphere at a time. So it can't really see the whole world so easily. So that does kind of limit. Hopefully, that limits how much it's memorizing things. But I'm not sure exactly if that's meaningful or not.
Okay, thanks.
Matthew.
Hey everyone. Hey, hopefully you can hear me. Hey Stephen, thanks so much for your talk. It was super interesting. I really like this all this kind of stuff. So I'm a severe weather meteorologist and a machine learning PhD student. So I work in Australia's equivalent of your storm prediction center. So we're really interested in like forecast time ranges from like 0 hours to 24, maybe 48 hours kind of thing. So these like really fast model runs are really exciting for us because you can just do them really quickly as the weather's evolving.
Yep.
I'm guessing one of the bottlenecks that would be like fast kind of real-time data assimilation.
Yep.
Do you have any comments on that, or is that something that you guys have been looking into at all?
So I think this is something that I think most of this field, like sort of the AI, it's kind of a pretty obvious next step, I think, for this sort of area of like AI weather prediction. I mean, this came up in my discussions with Craig, for example, but I think pretty much everybody that I've been talking to thinks that we need to figure out how to do data assimilation. And that's kind of like the big, right now we're kind of everything, all these models are bootstrapped on top of another data assimilation system. So typically you take ECWS data assimilation and you sort of feed it in. I imagine it should be relatively straightforward. I mean, again, if you have like the observations to build models that at the very least can sort of can add sort of a correction with like some sort of a neural network on top of that data assimilation. And I mean, in principle, I think that just like we sort of these models are speeding up sort of forecasting, I would imagine that we should build deep learning models should be able to do a pretty good job of data assimilation as well. I think it's mostly the challenge of gathering the data sets that has made this to be hard. I mean, part of the reason why these AI models have taken off is they're really valuable data sets like ERA5 that have already done all the hard work of homogenizing all these different all these different data sources together.
Yeah, cool. Yeah, that makes sense. So I guess the challenge would be like mapping like a set of observations and maybe like a forecast output to like some that looks like a reanalysis.
I mean, I think we're going to see it in the next couple of years, almost for sure. Especially from as organizations like ECWF and NOAA kind of move into the space. I think it's who have that data expertise. I think it's almost inevitable.
Yeah, cool. Awesome. Thanks for that.
Okay, well, we're at 11 a.m. or 11:01 a.m. So why don't we all thank Stephan one more time for a great, revolutionary stuff, really. Thanks so much for sharing it. And then Jara, what's the deal? Everyone leaves here, but Stephan stays on?
No, we've got a separate Zoom room for the ECR session.
Okay, so everybody
the
gets
ECRs can jump across to that.
Okay. All right. Bye, everyone.
Thanks, Greg.
Have a great
Thanks,
day.
everyone.
Cheers.